4 cladding types. You can see the burn-up ranges for these cladding types, approximately when they were last irradiated, and the manufacturer and the assembly design type. I also mentioned that we're going through the fuel selection process currently, and we expect to have that done, or at least a lot more refined by the end of this month.
I'm sorry for a second, going back to slide 10. So all the 32 fuel cell slots will be loaded?
Our initial plan right now is to load all 32, correct.
With high burn-up fuel?
We expect it to be all high burn-up fuel, because we do have some that are high burn-up fuel that is relatively cool by this time. So we don't see that there's a problem with heat load with the high burn-up fuel. However, it's still an evaluation of whether or not we should have a low burn-up fuel assembly or two in there also. So we haven't fully identified that yet.
When you say that the open fuel rod locations will be filled by solid stainless dummy rod, these are the sister rods that you're going to take and you're going to...
That is correct. If we have
with a solid...
Right. If we have to remove a sister rod from a fuel assembly that's planned for storage, we will backfill that one rod location with a solid stainless steel rod, so that there's no open water channel locations within the phase.
Okay. So, but in terms of the thermal behavior impact on the, adjacent rods, we don't think
that's significant at this point.
Thank you.
Any questions on the table? Okay, now getting into some licensing considerations. As you're aware, we plan on submitting an amendment to SNM 2507, that is North Anna's site-specific license. We have 27 TN32 casks currently on the pad. A TN32 cask is sure it's an older design cask, but it's the same type of environment of even some of the newer technology canisters. So the type of cask really doesn't matter, at least as we see it. It provides the same thermal characteristics as any other type design. The nice feature of the TN32 is the lid and the bolted lid design. So it gives a availability in the future of having a lid removed and fuel assemblies taken out without having to potentially destroy the canister if you unweld it. So having a lidded system is what we feel a superior aspect of the type of cask to be used. And as I pointed out in the picture, we have space for an additional cask on pad 1 at North Anna.
A question.
Yes.
It's learning for me. If you had a license for high burn up, you can use the same license for low burn up. Is that right? If in the future they got a license and they use that license,
there's usually an upper limit.
Yeah.
So they can just follow that limit, then can use for any house. Okay.
Question. TN is currently developing what we call a design and licensing basis document. It will address the changes to the analyses that were previously approved, the general license TN32 FSAR. This, as I mentioned, this cask was designed and built to that TN32 FSAR. There will be some changes to the analytical features within that FSAR, and the DLBD will address those changes. So really, this is going to be a cask that has the TN32 FSAR as the basis for analysis, along with the changes in the DLBD that support high burn-up storage. So it should provide a very complete technical basis for the cask when you have the FSAR and the DLBD together.
So, Tom, did the current site-specific just reference the 1021 FSAR for the cask properties?
Well, there's we increased the burn-up properties some time ago for the TN32 cask at North Anna. And to do that, we used the the FSAR, a very similar approach. We use the FSAR for 1021, incorporating that into the 40 to 45,000 burn-up casts, with additional changes to the thermal limits that were provided under our site-specific license.
So you're building on that document?
We build on that document, and it's a very similar process to what we did back in the early 2000s.
Okay, thank you.
So the DLBD and the TN32 FSAR by reference will form what we will call the full licensing basis for the cask in our license amendment request. Of course, the largest change is going to be the closure lid design. We plan to submit the DLBD with our license amendment request, and we would anticipate it would be a proprietary submittal. We also have other materials in storage that will be addressed in our license amendment request that we feel right now would include thermocouple lances, the thermocouple fuel assembly interface guides. We insert we insert these thermocouples after the cask is loaded, so you have to have some assurance that you come down from the lid and you actually get into the right location. So we have guides that are placed on top of the fuel assemblies, little funnels, if you want to call them in a simplistic form, that will actually guide that thermocouple into the right guide tube location. We also may use borated stainless steel rodlets in certain guide tube locations to provide additional hold down if needed during transportation. So any additional hold down that is needed, we want to make sure that we capture that during the loaded process, because we don't want to have to open up the cask again. We plan to perform a dry run of all the loading activities that are not typically performed with the TN32. We've demonstrated numerous times the loading of the TN32. There will be some changes in order to facilitate this cask, particularly having to do with the insertion of the thermocouple lances. So we plan to transfer the cask with water to the cask prep bay, which is the way we normally load our new homes casks right now, is we transfer the cask and water over to the bay. Previously, the way we used to load the TN32 is to drain the cask suspended over the pool, and drain it out and chase down with helium. We want to actually move the whole cask with the water into the prep bay. And what that does, it allows us to reduce dose rates, because we're going to be inserting thermocouples through the top, through those holes. That's access right down into the cavity. We want to make sure that we have sufficient shielding in place for our workers. We anticipate, as we do on our Surrey site-specific license, having separate tech specs related directly to this research and development cask. So we wouldn't have one set of tech specs for all casks. It gets a little cumbersome to manage that, but if you have the currently existing TN32 tech specs and then changes that need to be adapted for this particular cask to be captured in a set of separate technical specifications, we're used to that. We feel it's cleaner. It makes a line of demarcation, and we just feel it's a good way to go. One thing that's different with this cask that we plan to propose is a thermal soak period, and this is mentioned in the test plan. We plan to conduct this during the loading operations prior to final leak testing. And really what the thermal soak period is, it's estimated to be 2 to 3 weeks after drying, in which the cask is going through its thermal transit, and we'll be recording thermal data at a fairly frequent interval. So we capture the entire thermal transit from the time the thermocouples are inserted wet through the drying phase, so you know what the temperature increases are during the drying phase, and then you watch the temperature after the drying for a period of about 2 to 3 weeks until we come to thermal equilibrium. And we actually think we get to thermal equilibrium in about a week. That's just from a heuristic experience.
However, in the future, if you have different burn up, then how you assure that 2 weeks will be enough to this thermal equilibrium in the future?
Well, again, we're only looking to get to equilibrium. Our experience after loading these things, even with because really it's the temperature, it's the thermal loading capacity, and we've loaded TM32s, over 30 kilowatts. And this would be pretty close to that, what we've experienced. Our operators, as I said, as soon as we backfill with the helium, the temperature comes up really quickly, and so it's going to be, and that's really a matter of a day. So even though it's a large thermal inertia, you're largely at your equilibrium point very quickly.
So like you look at the bouncing case, and then you come in like 2 weeks. Is that right?
We haven't done any analysis for the 2 weeks. I'm just talking about what we've experienced during loading and how quickly that cask comes to temperature. And that's usually 1 week period. That we really think that 2 weeks would be sufficient, but we want to give ourselves a little bit in case we still see it dipping down in time. Maybe 3 weeks is what we would need.
Thank you.
So, and what we plan on doing, we have to monitor the cask during this period. Normally when we load a TM32 cask, we have a temporary alarm panel in the cask loading bay, and that gives us time to do all the cask work and all the prep work while the cask is being monitored on this temporary alarm panel until we actually take it out to the pad. Well, this is going to be a little bit longer, and so what we would do is and we haven't done our final leak testing yet, so we would use a pressure gauge hooked up directly to the cavity pressure and monitor that on a daily basis, so that we actually pressure reading. So we are doing the actual monitoring of the cask, but we're actually monitoring the true cavity pressure during that period of time. The reason, what we also want to do with this thermal soak period is to take a look at the cavity gas itself. We want to see, okay, how does the moisture behave in the cask during this period, and so we'll get an indication of how well the typical drying process that we use works. So we should be able to take sufficient number of gas samples to get moisture content over time. So we'll get a good picture of how the moisture in the cask behaves over time for this first initial 2 weeks, 2 to 3 weeks.
So this during this soak period, the cask is sitting. This operation, this is something that is different.
That's different, yes.
Right. That you coming in with this amendment.
That's correct.
That you need to look at the radiation protection.
Absolutely.
Calculations.
That is correct.
Who doesn't have this operation, this process?
It doesn't, but the feature of the of this cask, or actually the loading bay, is it is our resin loading area, so it's designed to handle the high dose areas or high dose rate. And we've talked with our radiation protection group there, and they would, during this period of time, set up protection limits and around that area so that we wouldn't have anybody going into that area without authorization.
Right. So in your application, this is what you have to...
We would address that, absolutely correct.
Address the reviewers, they're going to look at this.
Yes, since it is new and different, we would address that specifically, yes.
And those analyses would consider confinement effects and stuff like that?
Yes.
Leak testing has not yet been.
That's correct, yes.
And that would include, I guess, you need to look at any events not come into play. That's something you need to look at.
What events?
Well, you've got normal, off-normal, normally.
Oh, sure. Yes, I agree. Yes.
Off-normal events,
True. The other feature of the area is this is a monitored location with process vent, so it does take a look in case there's any type of release. It is monitored. So it is slightly different than the pad area. During the thermal soak period, we anticipate collecting cavity gas samples, and again, analyzing those for fission gas, hydrogen content, oxygen, and moisture. We'll also be able to determine what the pressure is, since we're monitoring the pressure on a daily basis.
I want to point out because your thermal data is very important for you to show the compliance with the regulation. So you need to make sure follow the guidelines to have the instrument calibration.
Right, yes.
Because that would be very important. We may look at that to make sure your instrument will function very well. So your data could be trusted. Because we have seen some cases in the application and they fail to do the calibration. So we do not accept their data. I mean, not your case.
Well, we don't feel that the data here are needed for the regulatory basis for the CAS. So they're probably non-safety except for the interface with the confinement area. So we want to make sure confinement's done, but the thermocouples are what's used in reactor, and they're not calibrated. I mean, it's a material itself, so we don't use a calibration on that. And being thermocouples, they're very rigorous and hardened for radiation areas. The other analyses that come in would be calibrated, using calibrated equipment for oxygen. Hydrogen would be done in our gas chromatography that we use in our lab. Moisture will have a calibrated system for moisture detection. Our fission gas is done with our multi-channel analyzer, very sensitive. It'll pick up whatever we need to see. And so those are all calibrated with our plant processes.
Okay, good.
Tom, did you say that you're not calibrating the thermocouples?
Well, they come in calibrated. We don't have a procedure for actually calibrating.
But they're going to be calibrated?
Yes, they're going to be. Yeah, they're going to be calibrated at fabrication time.
Okay.
Just wonder why you don't have the temperature here.
Well, this is for cavity gas.
Oh, okay.
That'll come with a temperature measurement. The moisture data will provide insight to the cast drying method. So we feel that that's going to be important data to have. And we're looking for some sensitive moisture measurement technology, and we're actually in the process of looking to develop that right now. We're looking for around 0.6 milligrams per liter, and in a helium environment, which is a little different than what you buy off the shelf for humidity type measurement, which is calibrated for air. So we want to make sure we have the right instrument for a helium environment. Okay, now we plan to do the final leak testing after we do this thermal soak period, and that's because the final leak testing is very sensitive to having helium inside the interseal space. It's probably not something that we're all familiar with, but once you have helium inside your interseal space, and in between the dual O-rings, you never really get it out. And so you don't have, before you put helium into this, you want to make sure you've done all your testing up front, and then you do your final leak testing to get down to the 10 to the minus 5 millibar liter per second criterion. So we will do all our final leak testing after this thermal soak period, right before we go out to the pad, which is the way we normally do that. And post-transfer to the pad, that's when we start our storage operations. We will have the same tech spec monitoring equipment through the overpressure system we have on our current TN32s. We will have pressure switches just like on our current TN32s, and we propose to have the same functional check frequency and monitoring as on the 27 CAS. And we perform the periodic checks there. It seems to be a good periodic frequency, and so that would fold in very quickly or very nicely with our current existing program. Our data logger, we plan to have that separate from the tech spec monitoring equipment. And the data logger will be monitored data, and they're not tech spec related. You know, getting the temperature data, we don't see any need to have that as a tech spec item. So that's all going to be non-tech spec recording data separately that we'll actually acquire on a periodic basis. We'll pull the cask probably twice daily, something like that, so we get the diurnal effect on temperatures. Of course, it could be more than that. We just don't want to have so much data that we're just flooded with it and don't know what to do with it. We want to get the right amount of data and the right type of data. And since we're doing periodic maintenance at the pad quarterly, that's a good time for operators to swap out a card or however we do it with Bluetooth, whatever the technology might be for that data logger, to acquire the data and transmit it so that we can get it out to the stakeholders. Now here's for the cavity gas sampling, and this is, there's been a lot of hand-wringing over this in the past several months, and we had some discussion back in January and came up with a method that we feel works. And we plan to do cavity gas sampling at the pad, which is different than in the past, but we feel we have a road to make this work. And so what we're proposing is to do the same type of an analyses for the cavity gas, fission gas, cavity pressure, hydrogen content, oxygen content, moisture, and it'll accompany with temperature data as well. And the way we would do that is to pull off the vent port cover, which will gain access to a quick connect fitting underneath. Now, when you do that, you breach the initial seal that you had. But when we pull off the vent port cover, we can actually grab samples of the cask cavity gas, and take them back into our lab for analysis. That part is easy. Where we've had difficulty in the past is that the cask at the pad is an unmonitored location. So we'd have to provide some means of monitoring that location in terms for radioactive material. So what we would do is, I'll get to our little picture that we have in here. Then we would reset, after we get the appropriate amount of gas from the cavity in the cask, we would take the port cover with a new O-ring, and it's a silver dual O-ring. The same design bolts and the same lubricant, the exact same process that we used to initially establish the 10 to minus 5 leak rate. And place that O-ring back on, but we would not be able to do a test that would show 10 to minus 5 because we've got helium in the system now, and when you use your mass spectrometer, it's going to detect trace amounts of helium that have been around it, and you're not going to be able to pass the test. And we know that. We've done that. And we've proven that. So what we would propose in our license amendment is that since we're using the exact same process with an identical O-ring that was initially met the 10 to minus 5 during our final leak test, we would place this, not do a 10 to minus 5 leak test, but rather do a sniff test around the outside there, and show that there's no helium leakage coming out. But the real bang for the buck is that this port is still monitored under the pressure, under the tech spec system, by the OP system. So you would make sure that your overpressure system is pressed back up to, say, 5.5 atmospheres, and it monitors that port. So if there is any bypass on that seal, we'll see it as part of our tech spec monitoring program that goes on.
I may miss some point. Every time when you perform the sampling, you take some gas out. That means you are going to reduce the helium in the canister. So are you going to fill helium back to the...
We would do that. Of course, we take out such a small amount, it's not going to really affect the overall pressure, but yeah, we would backfill at that time too.
What do you think about 3,000 liters at gas? Is that the free volume?
It's more than that. The actual free volume, I think, is about 5 cubic meters, and so at 2 atmospheres, so it's quite a large amount of gas. Yes, sir.
When you perform the sniff test, you can set that probe to still have a fairly sensitive
yes,
rate.
Yes, very sensitive. Yes.
So I guess you would probably want to make sure, though, that you have the proper procedures to make sure that you're not moving too fast.
Oh, absolutely. Yeah. We have the people who are trained to do that, and they would get their knowledge on how to go about that test.
Can you explain on slide 20 for your thermal monitoring? is that continuous monitoring for thermal monitoring? You've got penetration into the confinement barrier
That's correct.
with thermocouples.
Right. But the actual mechanical is below the seals. So the only thing that's brought out is the electrical connection.
This is a thermocouple that you have inside the cavity in the guide tube
That's correct.
that you're reading temperature from.
Yes.
Okay. So while the cask is sitting on the pad, so you do have a penetration into the confinement barrier.
Yes, we do. It's sealed penetration, right. It's the same type of penetration that's used in reactor with a 2,000-pound pressure difference.
Right. This is for our confinement folks that are
Right.
realizing that there is a penetration to the confinement barriers throughout the storage period. Or are you disconnecting this after?
No, we'll get into more of that into
Okay.
proprietary.
But the point is that there is a penetration, the thermocouple penetration.
There is a thermocouple penetration. Right. The mechanical portion, not the electrical, but the mechanical is all under the dual seals. The electrical comes through that penetration.
Yeah, but I mean the actual thermocouple that is inside the cavity in the guide tube, you've got the wires, coming
Right.
through the closure lead, which is part of the confinement barrier. Okay, so that's on the thermal monitoring. But on the gas sampling, you don't plan to do any continuous monitoring. It's just going through the vent port, I guess, periodically,
Right.
taking a sample from the cavity.
That's correct.
Okay, so that's it.
So there's
Thermal continuous,
thermal continuous gas periodic.
gas periodic.
Yes.
Okay.
I may be picky, but just wonder, when you perform the sampling, you draw out a small amount of gas. How you assure no small amount of gas will represent the entire gas condition in the because if you have very complicated configuration, then the gas may be not identical everywhere or mixed uniformly. So how you assure when you draw a little bit that could be used to represent the
Well, we'd have to follow our procedures for the gas bomb, and we do this routinely at the plant on pulling samples. And I'm not familiar with what that procedure is, but yeah, I'm sure you have this gas bomb. It's designed for pulling gas samples, and it's evacuated and dried. And so it's 0.6 liters, I believe, is the amount. So however amount we would need for our analysis, we would pull that number of gas bombs. And there is a